So good afternoon, everybody. Good morning or good evening. So we are today here for a new industrial talk. This series of talks are sponsored by IEEE Security System Society Rio Grande do Sul chapter and chapter of Calcium EDA Brazil and IEEE CAS chapter, Security System Society chapter Argentina. But today we are here to see the talk that will be given by Daniel Musciano from Allegro, Argentina, and the session chair will be Victor, and Victor is also working with Allegro, but he's the vice chair of IEEE Security System Society chapter Argentina. So Victor, thank you for accepting to be the session chair, and Daniel, thank you also to accept our invitation to give you this talk that I'm sure that is going to be very, very interesting to see what Allegro is doing in these 20 years of activity in Argentina. So Victor, the floor is with you.
Okay, thank you very much, Ricardo. Okay, well, as said, my name is Victor, I'm from Argentina. Today we're going to present about Allegro Microsystems, which is a company, world company, but today we're going to talk about what has been happening in Argentina in the last 20 years. Okay, Daniel Musciano is the layout manager in here, working with around 20 or 30 people. Correct me if I'm wrong. Mm-hmm. Okay, Daniel, all yours.
Yeah. Okay, thank you, Victor. As told by Victor, I'm one of the founders of the Design Center of Allegro in Argentina. I'm a senior IC layout engineering manager for the South America Design Center, since we also have one branch in Uruguay. We are going to be talking about this later. And I also part, since some years ago, part of what is called the innovation team in Allegro Microsystems. I'm in charge of all the layout developments inside the innovations for the Allegro Microsystems. We are going to be, this is the topics we are going to be including in today's talk. I'm going to be starting with a global corporate overview about Allegro Microsystems in general, not only in Argentina. Then the second part is going to be about which were our milestones or our history inside about the design center in South America. And finally, I'm going to be talking about some products which are fully development for the design center in Argentina. Global design from Argentina. Well, this is a very synthesis of what Allegro is in the semiconductor industry. Allegro has more than 30 years in innovation in semiconductors. It's #1 market share in magnetic sensor in integrated circuits. It has over 450 active US patents, more than 1 billion ICs shipped annually, more than 10,000 customers worldwide, and is one of the top suppliers of the automotive ICs. We are going to be talking about which are the major activities inside the automotive business we are providing our products. Allegro Microsystems is a company with a headquarters in New Hampshire, in Manchester, the city of Manchester in New Hampshire, United States. It has more than 3,900 employees. The global annual sales is around $700 million for last fiscal year. It is a projection for this one. And this last is kind of obsolete because it's saying that it's primarily it's privately held company, but since less than 1 month ago, we became public and we did our initial public offering in Wall Street, and now it's Allegro is a Nasdaq listed company now. About the main distribution of our products, we call them to be inside the actions for sensing, regulation, and driving. But basically, we are going to be dividing the family of products in two main branches, to put it simple. One is usually they dedicated for power or ICs, where with some kind of power management, and the second branch is all our family of integrated magnetic sensors, to have a very generic categorization of the products. We are going to be giving more details about the details on the distribution inside of these two branches. In the case of the power IC, in the first branch of the products that we got, we also have some internal division into those power IC into what is called motor drivers, and the second family, which is related to regulators and lighting. The motor drivers, so we have a very wide range of brushless and brush DC motors, or also for stepper motors. And also for the other family, we got a bunch of multi-output system regulators, or a family of LED drivers, which is also, as you may know, broadly used in many alternatives, not only in automotive, but also in industrial and consumer electronics. In the case of the second main branch of products for the company, we are talking about all of our family of integrated magnetic sensors. We have more than 30 years specialized in initially with Hall effect sensors, integrated Hall effect sensors, either planar or vertical. Planar, we are going to be talking about probably later of which is the difference between those two technologies. The same technology, but with different kind of activation of sensing, how is detected in the magnetic field in the chip. We have patented IPs in speed and current and position sensors for our integrated circuits. Also, we have some diverse patents related with the packages that we used to have for our, in some cases, not only an integrated magnetic sensor, but also a complete system, which includes the sensor, but also the magnet, just to be able to detect one magnetic field difference when the target is present before our chip. And more recently, we have our newer technologies on magnetic sensing devices, which are GMR and TMR magnetoresistors, which is also helping to expand our market position with our system, with our magnetic portfolio in the industries. Historically, more than the 80% is used for our magnetic position sensors was based on the automotive industry, but later the industrial and consumer electronics, more related with the current sensing and positions ICs, is getting is modifying that proportion. Basically, the applications that we use for our magnetic sensors are, as I said before, current sensing, linear and angle positions for either electric power steering or position of pedals or level measurements on the fuel tank, on all that stuff, and also with switches and latches. So basically, every single thing that is getting moved, that is needing to be detected in an automobile, is made by just putting one magnet and one magnetic sensor on the other end, and that's the way that usually every single movement in a car is detected. That's why, as this other slide is saying, any common car with a kind of full equipment is having probably more than 80 chips from Allegro in the different applications. As I said before, for camshaft sensor or crankshaft sensors, or throttle position, ABS, power windows, power doors, the wall speed, so headlights. So basically, now we have different alternatives for either what we call the comfort of the cabin of the car, but also for the more harsh environment, which is the where the motor is placed, or transmission. So that basically we have all these applications, and also during the last years, well, first of all, we are going to be mentioning these are all our clients. You can see that pretty much all the automotive industries are in here. And during the last years, we were also working heavily on what is the ADAS, or the automatic systems for driving, automatic driving of cars. Basically, we have a full suite of solutions for the ADAS on technology on the cars, either for the motor driving of electric cars, or what is generically called the HX, which can be hybrid or full electric cars. So that's kind of including or increasing basically the quantity of chips in a car in about probably 20 or 30 another units dedicated to what is the system, the different applications related with the electrical system of the new cars in hybrid and electrical vehicles. We have new applications like the driving for the batteries and all those. We have a lot of more current sensors, chips needed for this application on automatic driving. But also we have some other alternatives or some other applications that has to do with the processing and the detect. Basically, first of all, about the detection for this automatic driving. Talking about the detection is very recent, but Allegro has has bought a company that is dedicated to LiDAR technology for detection of for visual detection of obstacles and signals and complete, as I said before, the whole suite for applications on ADAS technology. Again, in addition to that, we also are developing our chips for green technologies. We have our current sensors and switches are multiple use in solar panels or motor drivers of robots and in e-bikes, they are used to call, but also in new technology or top of the art technology fans for for drives in data centers, which is very common for the companies to rely having all the data not in their proper servers, but in some particular data center where they migrate all their servers. But in some point in time or somewhere, all these files must be present in a drive. It's a company which is probably the only thing that is doing is providing drive storage for several companies, but the consumption of power for those drives is anyway. And this is pretty much the idea on these new technologies, where we are developing smaller and more effective systems to drive the models for that drives. Talking about a little on the global distribution of the company, depending on the color in the slide, you will see some what we call application support and technical centers and design centers. The design centers, we have two in US. One is in particular in the headquarters in Manchester, New Hampshire. Later out of the US, we have one other design center in Scotland, which is dedicated to power ICs. Then the next one in line was the design center here in Argentina. Later, we opened our branch in Uruguay, and then more recently, we have a couple of years ago one design center opening in Czech Republic, in Prague, and since the last probably November or December of 2019, we also opened one design center in Milan, in Italy, which is not present in this slide because this slide is kind of it's older than that date. About the technical centers, you can see that the location are France, Germany, Japan, Korea, China. So it's pretty much easy to realize that how important for us the automotive industry and the automotive business, because pretty much all the technical centers are right in the countries where by name we know most of the automotive companies are present, right? So in our company, we are working since several years ago due to the requirements to be on top of the requirements, but let's say from the automotive companies to go to a default, to a zero defects goal, right? Because it's all the quality standards in in the automotive industry are really high, and are pretty much with time getting more and more strict, and that's why the reason for the zero defects goal in our company since several years ago. We also are compliant with all the Japanese standards, and also with all of our later releases for the automotive industry are verifying what is called the ASIL quality standard which is the latest standard, which is agreed by the automotive companies. In here we have a little of history about which is our technologies, which is the evolution of our technology. Allegro has or had in the past in our own headquarters, we have our own foundry. Then by 2012, we just closed that foundry, and during some short period of time, we were a fabless company. And then and we were fabricating our chips mostly in a company which is called Polar Fab in Minnesota in US, and then the rest of our fabrication being made in UMC in Taiwan. But later on, the Polar Fab, the foundry in Minnesota, has been bought by Allegro, and now is part of our companies again. So we are now again a company with a proper with our own foundry. But even with that, even when we are fabricating probably chips in UMC and also now in TSMC, we also keep or we use our own receipt or our one process running in that foundries. We don't fabricate our chips with UMC processes or TSMC processes. We run our own process, our one receipt in their foundries, and fabricate our chip with our own rules, basically. Our current state-of-the-art process is 180 nanometer chip, so 0.18 micron. And it was an evolution from the 1.25 that we got in 2014, basically. It's a BCD process. It's a BITMOS process. And also we have several unique solutions, as I said before, around the packaging, making more efficient the application of the chips in the different situations for the needs of a car. As I said before, in this particular case, well, I don't know how to manage, how to point to what I was the second chip from the left. The second package on the left is what I was saying before, a chip that is including the magnet in the same package with the chip. So in front of you put this in front of our target, and then depending on the presence of a magnetic field or in the case of a gear tooth, you can detect the peak or the valley, and that thing is making a difference on the magnetic field, and that's what the chip is detecting, basically. And then we have the other alternatives that you can see is our different packaging, which are also several our own patents for integrated current sensor in the same chip, where the current is flowing through the package and not in a shunt version. It's basically we have the current flowing over this V of two very wide pins we have in our package. And this is basically, what I was saying before. The company has more than 450 active US patents, including different situations or different categories of the patent. We have patents that are related to our motor control algorithms or systems, for patents that are related to our current sensors, another patents related to our angle sensors, some about the speed, and in some particular case are just related with the packaging or the particular solutions that we find out for our package or transducers that we needed for our parts. Just an additional information that is not present in the slide is that from those 450 US patents that the whole company has worldwide, more than 50, I would say, probably almost 60 of them are developments from our design center in Argentina. So that was a kind of a quick overall of the Allegro microsystem worldwide. I'm going to be kind of talking about quickly about our milestones, our history, our line of our history line. During 2000, we are talking 2001. The idea is to just focus yourself in time in that moment. Let me see why it's not. By that moment, you might remember Mr. Bush was assuming the U.S. presidency. Another thing that was happening, unfortunately, was the attack to the World Trade Center by the Al Qaeda. We had another kind of not very interesting situation that we got in December. 10 presidents in less than 10 days in our country, which was kind of funny, but it was not very funny at all at that moment. If we are talking about the technical scenario of that days, in hardware, we got Apple presenting the first generation of the iPod, and Microsoft introducing the Xbox. In the terms of software, Microsoft was presenting the Windows XP, and Apple launched the Mac OS X. So every time we have those two companies getting some fight between them, getting some innovation. Talking about the semiconductor industry scenario, by that days, we got the state of the art on that moment for most of the high-tech companies was the 130 nanometers lithography, like it's saying the process PX60 of Intel or the CS91 from Fujitsu. So basically, it's really interesting to see that the state of the art of where in the moment where we were kind of starting our design center in Argentina, all these guys were already having something less than, smaller than the process that we have nowadays, right? That's kind of showing that it's not needed for a lot of applications. It's not needed to be on top of the wave or on the state of the art of the industry. By that moment we were having a node size that it was probably 500 0.5 microns or two, no more than that. It was 2 microns, something like that. It was really big, but you can still have a very good business and a lot of applications with nodes that are really far from being the state of the art of Intel and AMD. In the case of Intel, well, that's what I was saying. It was 130. So by the moment, 2001, we got 5 crazy guys, which decided to, from the University of Buenos Aires in Argentina, we were deciding to open one design center in Argentina. You can see second from right, a very good-looking younger version of me, and then plus we were all as I said before, engineers from the University of Buenos Aires, plus Alberto Bellori, which is the guy on the second row, the photo on the second row. He was an external consultant for Allegro Microsystems since the 90s. Really crazy to think that he was a designer of integrated circuits in days where the communication was made by the previous version of what we were, many of you might know as which is the fax. No, he was doing the thing by telex, which was kind of an SMS, but just by a telephone line. You know, it was really crazy to think about that he was doing design of microelectronics with that system. By that moment, as I said before, we were doing the whole design process of integrated magnetic field sensors in CMOS and BIMOS technologies. And our node was, that was the number, I didn't remember the moment, it was 1.25. So it was 1,250 nanometers. That was the node size we were using by that days. Then that was in 2002. In 2001, in 2002, we hired our first evaluation engineer, and then officially we opened our measurements lab, including the ultimate technology for wafers and package parts measurements, and in particular by trying to measure microvolts and nanoamps and all those and nanovolts also. We realized that trying to make the thing in the middle of a city like Buenos Aires is not that easy, you know, by the hard way. We realized about that. We saw that the noise that we were having in the air was just orders of magnitude bigger than the thing that we were trying to detect. So basically, that's why we started by measurements, our measurements or our delicate or particular difficult measurements in the parking lot of the building and in the underground as a first alternative, until we finally got into the build of a Faraday cage, as is shown in the picture of the middle. Okay. Oh. Then our next step in our history was the hiring of a second layout engineer. By that moment, I was the first one in 2001. But in 2005, I hired a guy who was supposed to assist me, and finally I got him in charge of the layout portion of all the power devices divisions from Argentina. Then the next step was in 2000, and the next milestone in our history was in 2009 when we finally started our digital design team by hiring 2 engineers. One was from the University of Buenos Aires, but the second was one guy from Argentina, which was a former employee from Intel Israel, and who was returning to our country for personal reasons, and basically we just got the he came into our company in the right moment and in the right place. So it was kind of a very interesting coincidence. In 2010, we finally moved into our new offices, which is our current location. From compare what we were having until that moment, that allowed us to have a 4x growth in headcount employees, which was a very big bet from our side. But finally, just we already got into the situation to have the total area of this new place also kind of short in area since a couple of years ago. Then later on that, in 2014, we started a local division with device modeling for our components and for the components used in our devices, in our chips. We just hired 1 engineer and one PhD in physics. And nowadays in Argentina, our modeling team in Argentina is the only location where Allegro is doing device modeling out of US. And the unique location where Allegro is doing modeling for the new technology of TMR and GMR sensors, magnetic sensors. So we are doing the modeling of those magnetic sensors for the whole company from our country. In 2000, I said before, in 2016, we opened a branch in Montevideo in Uruguay. It also started with the 5 engineers doing analog designs and layout, and currently has a headcount of approximately 15 employees as well. That's how we got into what I used to mention with this drawing. What are the 5 main pillars for the IC design of a chip? It's the analog design, the analog layout, the product evaluation, the digital and design verification, and the devices modeling. These are the 5 main stages or 5 main groups needed for an IC design. With the time, we were adding into our ecosystem and our design center the different portions that we were needing to just now have a complete solution for being able to get a final product from a design intent or from a data sheet from the beginning of the days of a chip. That's how we finally were able to get into these. I guess it's 4 cases that I brought today for this presentation. As I said in the very beginning, this is our 3rd and final part of the presentation. We are going to be talking briefly about several parts, which were full development from the design team in Argentina and Uruguay. The first of all is what is called the part number is the 1160. Is a Hall effect switch. It has the characteristic or the feature to have a built-in self-test. How is that? Okay, what we have is as I said before, we work with with two different technologies of Hall effect sensors. One is the planar Hall effect, and the other is the vertical Hall effect. The planar Hall effect is a sensor that is going to be detecting a magnetic field that is going to be perpendicular to the face of the chip. So, and basically, what this chip has is on top of the sensor, it has a coil. Basically, it has a metal all around our magnetic sensor. Every time that we excite that, we have a current flowing over that coil, it's going to be generating one magnetic sensor, of course, and that's a known version, a known value of magnetic sensor, which is the fact that we use in this particular chip. When we send the chip to self-calibration, it's going to be running an algorithm that is going to be flowing the current in there, knowing it already knows the field, the magnetic field that it should be measuring, and based on that, it makes all the adjustments. In terms of the function, well, it's as I said in the title, it's a Hall effect switch. So it's basically a switch that on-off, changing from on to off in the case of a presence of a magnetic field, but in particular with the chance to be self-testing. I have the capture of the layout for this chip. You can see in the middle, right in the center of the image, the two light blue squares. That are the coils that I mentioned we have on top of our dual sensor. We have two sensors in the center of the chip, and all this functionality is present in a chip that it has 1.11 by 1.3 millimeters. So it's 1,118 microns by 1338 microns. So it's pretty much a little more than 1.1 or 1.2 square millimeters to have this functionality. The next step is, well, we started to combine what we got our initial technology of magnetic sensor, which was the planar Hall plate, with the second version of the Hall plate sensors that we developed in our design center, which are the vertical Hall plates. The vertical Hall plates are going to be, before I said that the planar is detecting a magnetic field that is perpendicular to the field of the chip. Well, the vertical Hall is going to be detecting a magnetic field that is parallel to the face of the chip. In particular, if I put two vertical sensors with a 90 degrees separation, we are going to be having X and Y measurement of magnetic fields. In the case of the Allegro 1266 magnetic sensor, is a 3D magnetic sensor. Basically, we have two vertical Hall plates in 90 degrees position difference, and also a planar Hall plate, which is going to be detecting the magnetic field in the Z direction, so vertical or perpendicular to the chip. In terms of in practice, what this chip is going to be making is going to be detecting the presence or not of a magnetic sensor in the area of a cube, in the volume of a, I'm sorry, not in the area, in the volume of a cube. Which is the target for that? Well, as the target application, as is saying in the slide, was for tamper detection, of basically detecting if someone is making some trick or put some hand into smart meters for the electricity. That was the former requirement for the initial client that we got for this chip. It was an electrical company in China that was trying to detect some frost that they were having on smart meters caused by the users. So they got the guy going with that stick with our sensor in the point of the stick, and with that they were able to detect if there was some kind of magnetic treatment or tamper in the smart meter. After that, well, the same thing can be used to detect tampers in ATMs, in ticket machines, in electronic locks, or in everything or every electronic device that can be tampered by magnetic devices. In the case of this chip, again, it's basically a sensor, it's a switch. And the die size for this chip was even a little smaller than the first one. It's 1.1 by 1.1. It's a complete square of pretty little more than one square millimeter. The next case that I brought today is our first programmable angle sensor we got into our family of products. It's basically a magnetic sensor with a linear output, which can be analog or PWM, which is proportional to the angle that is detected by the device. How this is working? Well, basically, as I mentioned before, the vertical Hall plate detects one magnetic field that is parallel to the face of the chip. In particular, we were talking about sensors placed in 90 degrees, so one in the X direction, one in the Y direction. Well, basically, what is doing this technology of angle sensing is using what we call the circular vertical Hall. Basically, what we use is different vertical Hall pickups, but not in only 90 degrees. We have a total of, depending the case, 64 or also 128 vertical Hall pickups, just with small angle divisions or increments, making a whole circle. And with some proprietary algorithm and procedure, we got these pickups in groups of 5, and we process the signal in order to detect where the position of which is the angle of the position of the magnet, and it had a complete system of switches that is getting this group of five pickups, just making the whole round to detect the position of the magnet. It allows us to get the target application for this angle sensor is position of the pedal for either the accelerator or the brake in the car, fuel tank sensing, the level of the fuel tank, the gear position, the actuator of the throttle valve, so the input of air for the mix of air and fuel where the spark is getting generated in the car. All those are the different applications for this magnetic sensor, for this angle sensor chip. As here we have a capture of the layout. In kind of in the middle, you can see this circular sensor that I mentioned is our circular vertical hole. All these 4 areas around it are the switches that I mentioned that we used to have. We used for switching the signal along these pickups or these sensors. And all this L-shaped big area is the whole digital system, which is controlling the functionality of the algorithm that used for the measurement of the area or the measurement of the angle of the chip. Again, as in the other cases, I got an indication of the die size for this. We have all these angle sensor with programmable outputs in a total of 2.2 by 1.8 millimeters. So it's a very, very small thing anyway. And as I mentioned before, one of the applications is the position of the valve, which is controlling the input of air in this case, in this carburetor, as we used to call it before in the old days. This in particular case was the supplier for this was Bosch, and it's for an SUV, for a China SUV. It's a Chang'an 75. So basically, you have this movement being detected by, here is the chip, where when this cover is put in place, this chip is just in front of this magnet, and here is how it detects the position of the valve. And then last but not least, as I mentioned before, that we were top suppliers of magnetic sensors in automotive industry for years, and also we got into the LED and in our power IC device division. We got several years ago into it started in 2005 or 6. Our initial version of an LED driver chip. So in some moment we got someone thinking about, why don't just we make something hybrid, or we just integrate everything into one single chip. And that's how we got into the world first LED driver with an integrated Hall effect switch. This has been done in 2015, I guess, like something like that. I don't quite remember. But it's really the first time one company provided a unique solution with the actuator and the sensing device for controlling a LED3 in several applications. Basically, I'm gonna be going into detail into the characteristic or features that this chip has that allow us to have a very interesting portfolio or list of applications where this can be used. In particular, the most important or the most successful application for this chip were the white goods in like refrigerators and washing machines, consumer electronics. But in particular, which was the initial development for all this, was the automotive interior and auxiliary lighting. In particular, the features of the chip, it has a 150 milliamp LED driver integrated with a Hall effect switch. That makes a really smaller bill of materials when the final consumer or a final user needs to give a solution to application like this. The interesting is that this chip has several pins that allows you to give some particular features. One pin is prepared to put on that one resistor that is going to be working as a limiter for the maximum current for the brightness, for the maximum brightness of the LEDs. Another pin is going to be allowing you to put a cap on it, and then in that way it's going to be generating one tau or some time that is going to be creating or allowing you to create a fading in and fading or out in the turn on and turn off of the light. And also we got another thing that is going to be working as an external trigger. Why that? Okay, because even when this is really small, I'm going to be showing the area later, is more expensive. We are talking about cents, right? The cents of dollar, but so in volume. But anyway, a very simple switch on off is really cheaper than this one. So the idea is that this chip allows you to generate, in the case of a car, one system where only one door is going to be having this complete chip with the Hall effect switch and the LED driver, but all the rest of the doors can have a very simple switch that's going to be sending the trigger signal to this one to turn on the lights when the door is open. So these are the main characteristic of this first LED driver. The whole area in here is 1.6 by 1.1 millimeters. We got all these. The right portion is the LED, the Hall effect switch with the Hall effect sensor, dual Hall effect sensor in the middle. And on the left, we have by this area, by this location is the division. Pretty much everything on the right is the Hall effect switch, and the blocks on the left are the LED drivers. What is driving the LED? Okay, and this is pretty much it. Any questions or comments or whatever? Thank you for attending.
Thank you, Daniel. Okay, you can write all your comments in the comments tab in the YouTube. Please add any questions you may have.
There were a lot. I was just saying the tab of the private chat, so I was saying nothing.
Yeah, you need to see the comments. I have one question. You mentioned in the 1160 chip that it was center, but I saw a little shift there in the sensor. Do you adjust that in the package, or how?
No. Well, I was mentioning center just as a reference of Well, in this one you can see it's really in the center. That's correct. But in the 1160, let me go back. Maybe I just mentioned the thing just for reference. No, that's correct. It's not centered. It's, I just mentioned that thing as a reference, but it's not completely centered. No, no. In this particular case, I don't remember that we needed to compensate the location of the whole sensor in the package and shift the die inside the package. This is, as I said before, it's a very low cost chip. This kind of particular placements, shift placement of chips inside the package are more present in applications for where the accuracy is really more needed or a concern. We are talking here that it's a very simple on-off switch, and this is not a very important thing to have it completely centered on the middle of the package.
Okay. Okay, we are having questions. So the first one, when you refer to 3D circuits, the technology used was a 3D one?
It's not 3D from the point of view that from another thing that is called 3D, which is in many cases we call 3D in the semi industry when we have more than one chip in the same package. It's not the case in this particular chip. We call 3D from the point of view that is detecting a magnetic field in the 3 dimensions. That's why it's called 3D. As I said before, the idea of having two vertical hole plates and one planar hole plate is to detect the presence of a magnetic field in the volume of a cube. That's the portion. That's the reason that this chip is called 3D. In general, the chips are supposed to be in a particular position, just close enough to be able to detect the presence of a magnetic field. But usually it's in this direction or in this direction or on perpendicular direction to the chip. But the only interesting or the only reason in there is to detect is to be more immune to the distance or to the magnetic field. That's why we are trying to detect a volume in 3 dimensions, but it's different from the other 3D thing that is used to mention or called as jargon in the industry. We also have these kind of chips in some very preliminary. Just to answer, give a little more information to the answer. Some preliminary. One of the ASIL requirements is to have, in many cases, redundancy to some particular functionality of a chip. In some cases, the redundancy of function of solution to that chip is sometimes to put two chips, exactly the same chips in the same package. In a 3D dimension, in what is called a 3D package, having more than one device in the same chip. That is requires some technologies just to be able to have more than one chip on top of the other, and being able to both of them have both of them bonded to the pins of the package.
I know that can be tricky.
Yeah, really tricky.
So another question. Can you talk about which EDA tools are you using?
Yes, we use Cadence suite since we started with Allegro in 2001. Previous to our days in Allegro, Allegro was using Mentor, but since 2000 before 2000, probably during the 90s, Allegro migrated into Cadence and is using that suite since that moment. But mainly we use that. Mainly we use Cadence. In particular, in some particular occasions, mostly when we are dealing with another foundry for making tests with some foundry to start investigating if we can run our process into their fab. Sometimes we need to get into some other providers. In particular, I've been able to also use Calibre and some other versions and some other stuff. But in general, all these chips are with Cadence.
Okay. Yeah, Cadence is terrible tool. It's really excellent. I used to do layout in not Mentor, the other one, Tanet. That was
horrible. Well, I in particular, I was not able to do it. I know that many of you probably did. But yeah, I guess that anyone can have pros and cons. In particular, what I know is that at the very end of as soon as you get close into the foundry, they go more with the Mentor suites, with the Calibre and all those versions, all those softwares. But well, I don't know. Anyway, companies used to sometimes used to have several providers. By now, we are having just Cadence. I knew something that we might be eventually doing some tests to be using Calibre or Mentor things as a second provider in some point in the future, but nothing confirmed yet.
Okay, thank you. Okay, last question, at least for now. In which technologies are you doing designs?
Well, I mentioned very quickly before. In our case, is our own process. You know, as I said, as I used to say, it's our recipe. Basically, we fabricate our chips. I used to make one comparison every time. What I used to say is that I'm gonna be going to your house. I'm gonna be cooking the dinner, but I'm gonna be having my recipe. I'm gonna be having my ingredients, my recipe, all from. I'm not gonna be using. I'm gonna be just using your facility for cooking my stuff. That's it. That's our case, independently on where we are fabricating our chips. In particular, in our own foundry now in Minnesota, but also the same thing in UMC and TSMC. Our technology is a BIMOS with a 0.18 microns, 180 nanometers.
Okay, that's the
to just give a little more of detail. It has a standard backend of metals between 4 and 7. We have up to 7 metal layers of interconnection. Dual poly with a chance of having floating gates, or like what we need is needed for EEPROMs and flash memories, which is also part of the the PDK that we have for our processes.
Okay, thank you. We have no more questions for now. Yeah, I think we're on time. One last question, just to close. Is it true that you used to debug DRC by hand?
Oh yeah, in the old days, yeah, it was. Well, I in my particular case, I arrived to the days where it was not by hand. I needed to go into a very I needed to go into a very long process, but not by hand. It was but just for a few years. I just probably 5 or 4 years before I get into the business. I know that people was doing the thing by hand. In my case, I was needing to get some interaction or some iterations between generating one GDS, running a script, seeing how the thing was mismatching, and extracting. Extracting both the layout and the schematic, generating a GDS, running a script to compare things, checking whatever was okay or not, and then when you were having a mismatch, by that moment you got two alternatives. You were able to adjust the layout. Just in the case of a resistor, basically, you were expecting probably 1% of mismatch, and we were having 1.2. Well, we were able to really adjust the length of the resistor, or basically just tweak the schematic to just what present on the layout, because you didn't want to change the layout. So, but by that moment, we got that flexibility, and now the pieces are kind of more strict on what they allow us to do or not.
Okay, thank you very much, Daniel.